Hello and welcome to lesson 3 of unit 2. In this lesson, we're going to start uncovering the rules for differentiation. So that's why we have this titled part 1, because there are a lot of rules and we're going to talk about a couple of them today. So the first one is the power rule. And then we'll also look at what I call properties of differentiation, because they apply to really all of the rules, but the constant rule, sum, difference, constant multiple rule. And then we're also going to be looking at applying rules for sine, cosine, and tangent. So the derivative of sine, the derivative of cosine, and the derivative of tangent, which I threw in here because they're pretty straightforward. They're really just things that we have to kind of memorize. So they're not too difficult, and there is a little tricks and stuff that you can use to get those memorized. So let's jump in here. The power rule. So I have the power rule over here on the right, and we're going to uncover the conclusion here. So given a function x raised to some power, what is the derivative? So we're going to apply the definition of derivative to this function, x raised to the power of n. And of course, n could be any rational value in this case. Okay. Now, evaluating x plus delta x to the power of n does require a little bit of knowledge of the binomial theorem. And so you may have had some instruction on the binomial theorem in your prior class, whether it was Analysis 1, pre-calculus, potentially, or Algebra 2, if it was an honors class. But just to recap, the binomial theorem is a theorem that gives us a strategy for expanding a binomial, which is what this is. It's one variable plus another variable raised to a power. Okay? And what the binomial theorem does is it yields this mess here. The notation n over 1 in the parentheses here, that is a notation that represents a combination. So it's the number of ways we can choose one thing from n things. So if I had n marbles, how many ways could I choose one marble? This notation is the same thing. How many ways could I choose 2 of n things? If I had n marbles, how many ways could I pick 2 different marbles? Okay. And that notation is just a natural phenomenon that comes out in the binomial theorem. And it's not necessarily an important concept in our class, but it is used here in the derivation of this differentiation rule. So I used it, and if you have more questions about it, I can put a link in Schoology that will send you to a video to explain the binomial theorem. But again, it's not a necessary understanding for this class. Okay. So all I've done in this next step is sort of rearrange things. I've moved this minus x to the n to the front because I know it's going to cancel with this x to the n. And out of each of these terms that has, notice there's a dot, dot, dot here because there's actually a lot of terms here, right? I have factored out one factor of the delta x because there's going to be a delta x in each of these terms. So I have factored out a delta x. And so this becomes, there no more delta x in this term. This delta x's power has been reduced by 1, and so on and so forth, all the way up to the last term with delta x in it, delta x to the n, which becomes delta x to the n minus 1. All right. So now we can see that the delta x that I factored out cancels with the delta x in the denominator. The x minus n's go away because that's 0. Okay. And then I have just rewritten this combination notation in its sort of definitive in its sort of the definition of what that combination is. So for instance, the number of ways that I can choose one thing from n things, well, it's n. If I had 100 marbles and I said, how many ways can I pick one marble? Well, it's 100. So how many ways can I pick one thing from n things? Well, it's n things. N choose 2. is just a formula that represents the n combinations of 2, right? Or the combination of n two things chosen from a group of n. Okay. So what we'll see now is that every term except for the first term here, every term has a delta x in it. And since we're taking the limit as delta x approaches 0, the only term that's left is this first one, which is n times x to the n minus 1, which is exactly the rule or the power rule for the derivative of x to the n. A lot of times the way students think about the power rule is you take the power, move it to the front and multiply, and then decrease the power by 1. This explanation here is for those who are super interested in where this rule comes from. It's not a necessary understanding, but it is kind of a fun proof to do. So some properties of derivatives. So we have the constant rule. The derivative of a constant is just 0. We think about if you were to graph a constant, y equals 12, that's just a straight horizontal line. What's the slope? It's 0 everywhere. The constant multiple rule. So if I have some multiple times a function, the derivative is that multiple c times the derivative of f of x. The difference rule. If I have two functions that are being subtracted from each other, the derivative of that function as a whole is just the difference of their derivatives. And similarly for the sum. If I have two functions that are being added together, the derivative of the sum of those functions is the sum of their derivatives. Okay. And the last rules that we're going to talk about today are the basic trig function rules. So the derivative of sine is cosine. The derivative of cosine is negative sine, and the derivative of tangent is secant squared. Okay. So when we talk about more trig functions in the next lesson, I will show you a little trick for remembering the derivative of sine, cosine, tangent, secant, cosecant, and cosecant. But these are derivative rules that we sort of need to know by heart. You can start creating some flashcards. I will, by the end of this unit, once we've covered more of the differentiation rules, I will give you a list of the differentiation rules that you can use to study and reference. But yeah, we need to memorize these. So only one example this time, because it's really just how do we apply these rules. So in part A, we have a function f of x is equal to x cubed plus 3x. So we're using the power rule, the constant multiple rule, and the sum rule here. We have the sum of two functions, x cubed and 3x. So all the sum rule really says is I can find the derivative of those two functions separately and add their derivatives to get the total derivative. Okay. So for the power rule, we're taking x cubed, multiplying by the old power, which is 3, and decreasing the power by 1 to 2. For x to 3 times x, remember we think about this really as x to the first power. So I'm moving the 1 to the front, multiplying by 3, and then the new power is x to the 0, which is just 1. So I just get 3. Another way to think about this is, remember, the derivative represents the slope of a curve at any value of x. And the function 3x is just a line with a slope of 3. So what's its derivative? Well, it's just 3. Okay. For part B, we have two trig functions, sine x and cosine x. Pause the video now and see if you can remember what the derivative of sine and cosine is. Okay. So the derivative of sine is cosine x, and the derivative of cosine x is negative sine x. So we're using the sine, cosine rules, and of course the sum rule here, because we have the sum of two functions, sine and cosine, and ultimately we're just adding the derivatives to get the derivative of the total function. So part C, you actually might recognize or remember that we did use the definition of derivative to find the derivative of this function in the previous lesson. So we have the square root of x, and this sometimes throws students for a loop because they think, well, it doesn't look like any of the rules that I know. But remember that the square root of x can be treated as a power. That's x to the 1/2. So we multiply by that old power of 1/2 and decrease the power by 1. Well, 1/2 minus 1 is negative 1/2, which drops that x to the 1/2 to the denominator. So we get 1/2 square roots of x. And we're just using the power rule there. That's just a straight application of the power rule. So the next part, we have the sum or difference of three different functions: tangent, 3x squared, and 12. So the derivative there, we're using the tangent rule, the power rule, the constant multiple rule, the constant rule, and the difference rule. So all of the rules were used here. And eventually this will become something that is sort of second nature. You won't be thinking about the rules that you're using. You'll just recognize what the derivative of a function is. So for tangent x, the derivative is secant squared x. For 3x squared, we're multiplying by the old power. So 3 times 2 is 6, and decreasing the power by 1. So x to the first. And then plus 12. That's just a constant, and its derivative is always going to be 0. So that's why that term disappeared. So in summary, differentiating certain functions is fairly easy once you know the defined rules. We no longer have to use the definition of derivative to find the derivative of these functions for which we know rules. In the upcoming lessons, we'll uncover other rules for differentiation. This is a really sort of foundational unit in this course because moving forward, we'll be looking at applications of derivatives, in two separate units, and knowing how to find the derivative of a function quickly and efficiently, that all comes from this unit. So we want to be really, really quick and efficient with differentiating functions using these rules. Thanks for watching, and I will see you in the next video.